Okay, everyone, do you want to find a seat for those people still coming in? And for the rest of you, if you want to keep quiet now, because we have quite a bit to get through today. Are you all feeling happy? Yes? No? Well, I'm afraid you definitely won't be by the end of today. So this is my most depressing lecture. Every quarter I have to give this at least once. And it never really changes, and I never really get any happier. But we'll get through it, and then for the rest of the quarter after today, we're really going to be moving on to talking about snow and ice and glaciers and sea ice and things like that. So this is the last of our really sort of introductory lectures to understand the cryosphere. So really today we're going to talk about future climate change. And even if you never take a science class again, if you sort of give up after today, I really hope that whatever we talk about today stays with you. Shh. You need to stop talking now that I am, please. So, because really what we're going to talk about today is what our world is going to be like by 2100. And that has importance for every single one of us in this room. We're not immune from the changes that are going to happen just because we live in a nice sort of warm place. So before we get started though, a bunch of announcements. So quiz 2 is available this weekend. Because we don't have any classes on Monday, I'm going to extend it to the start of class on Wednesday, so you have lots of extra time to do the quiz this week. And so there's a couple of extra little tricky questions in there. There are no discussion groups on Monday. So for anyone who has a Monday discussion group, you should have got an email from me already, but you are welcome to go to a different discussion group next week if you would like, because I don't want you to miss out on the opportunity to do the activity and to ask questions if you have any. So you can go to any of them next week if you're on a Monday discussion group. The reading is up there for this week. It's just that chapter 3, which basically explains a lot of what we've been doing this week about climate change. And I also had a request from a couple of students who asked for an introductory sort of book that covers things like what energy is and what matter is. Some of those, the more background information that might not be included in the UN report. And so this is the book I used for ESS 1, which is the introductory Earth System Science course in fall. And there are now 5 or 6 copies of this, I think, in the library, the science library. And you can take it out for a couple of hours at a time. And it has things like what energy is, what matter is, things about the planetary energy balance. It has a chapter on the climate system with a lot of the information from this week. So for the ice and snow, we're really going to be focusing on that UN report. But if you want to go back into more detail about what elements are and things like that, then this is a really good book for that. So if you would like an extra resource, this is now in the science library. Okay? So is that all of my announcements? I think that is. So let's move on to more exciting things. So at the end of the last class, we basically ran through somewhat of a list of how our climate has been changing. This isn't something that how our climate might change in the future. We are already seeing changes. We've seen increases in temperature of our atmosphere, of our ocean, even down to the deep ocean in some places. We've seen changes in the pH of the ocean. We're seeing changes in the amount of ice and snow on our planet. So all of these things are already happening. And the question is, or the very big question, at least for the last sort of 30 or 40 years, is why? Why are we seeing such dramatic changes that we haven't observed for sort of centuries on Earth? And these were the list of the things are 7 reasons why climate on Earth has changed in the past and why it can change. So looking at those 7, I have a question for you. We can discount at least 2 of those. If we're just thinking about why climate has changed over the last 100 years, why it might change in the next 100 years, we can safely ignore 2 of those. Which 2 of those do you think we could safely ignore? So have a look down the list, remind yourself what those are. Consult your neighbor. Okay. So once you've made your decision, let me know what you think. Any more answers? So vote if you haven't had a chance to. So let's see how awake we are today on a nice Friday afternoon. 2 and 6 is the popular answer, and that is the correct answer. Well done, guys. So really, if we're looking at that nice long list, we can only ignore 2 of them, really. We can ignore the distribution of continents. Well, we can't ignore the fact that they are where they are, but we can ignore the fact that they might be changing, because they are changing ever so slightly. Do you know that New York is moving apart from sort of London at about 2.5 centimeters per year, which is about as fast as your fingernails grow if you didn't cut them for a year. But really, those aren't dramatic changes. They're not going to have a huge impact on our climate system in just 100 years. And the 6th one, that changes in Earth's orbit, there's really complicated cycles of eccentricity, so how elliptical our orbit is, of obliquity, which is how tilted we are, and precession. All of those happen on sort of 20, 40, 100,000 year timescales. So even if they are having an impact, it's going to be a tiny, tiny, tiny impact compared to those other things. So really, if we want to find a reason why our climate has changed so dramatically, we have to look at those other 5 or so. So solar output, surface characteristics, greenhouse gases, aerosols, and feedbacks. Okay. So if we take a look at a couple of those, for example, we have some things on there that we clearly have no influence over. So we have no influence over whether a volcano erupts or not. That's a completely natural thing that can affect our climate system. We also have absolutely no impact on the solar luminosity on that, say, 11-year sunspot cycle. It doesn't care that we're here. It's going to do it anyway. So those sorts of things we call natural forcings. And if we look at what's happened with those, if we run our climate models, we get that sort of blue area on here. And so the map here shows the temperature record for different continents, and then for global land, and global ocean. The black line is our instrumental record. It stretches from 1900 up to 2000. If we look at just natural forcings and run our climate models, then what they sort of put out is that little blue shaded area. And they really can't explain. They may have been able to explain some of why climate was changing earlier last century, but it certainly can't explain that increase in temperature that we saw in the last 30, 40 years or so. What we have to do is, if we add in what we call anthropogenic forcings, which are the things that we have an influence on, things like our increased greenhouse gases because we're putting CO2 into the atmosphere, things like aerosols, the fact that we have more soot in the atmosphere because we're burning more sort of forest fires which put ash into the atmosphere, things like surface changes, deforesting large areas. If we take those changes into account and run our models, now we get the pink area. And you can see that now our climate models seem to be representing much, much, much better our instrumental records. Doesn't mean that we're going to give up and say we've solved it and we're not going to continue taking observations and refining that. But really, we can't explain what we've been seeing. There is no way we can explain what we've been seeing with our climate with just those natural forcings. So really, in terms of the big questions that we have about climate change, are we causing it? Absolutely. There really isn't much debate about that anymore. It's really pretty certain. Because we can break it down even further to look at more carefully what things might be affecting. So this is taken from, you know, that gigantic report that I brought last time and didn't want to bring this time. So the science space is on there. This is the one from the last report that came out in 2007. And you can see that my line there goes across at 0. Above that, anything above that is causing warming of our climate. Anything below that 0 is causing a cooling of our climate. And then also at the bottom, we have the level of scientific understanding, and we go all the way from high, we understand greenhouse gases, to very low, we don't really understand why the sun does what it does. Okay? And you can see that really, if you look at all of those different columns for the different things like aerosols, for solar variability, for land use change, for surface characteristics, there's one that stands out pretty much, right? Which is our big greenhouse gases. They are by far adding the most energy. In your discussion groups this week, you had fun with numbers, right? And you added all of those sort of formulas together, and you sort of worked out our planetary energy balance. What we're saying, what that column represents, is an extra watt per meter squared. Okay? So if we add up all of our greenhouse gases, you can see we have an extra 2.5 watts per meter squared on the Earth's surface, which is sort of a result of that greenhouse gas. And it doesn't sound very much, but remember it's over the whole Earth. And so I have a really nice analogy, which is from one of the lecturers in our department. How much energy is that? It's the equivalent of putting a little Christmas tree light on every square meter of the Earth's surface. And so they don't give out an enormous amount of energy, but you can feel that there's this, like when you touch them at Christmas, they feel warm, right? So that's how much warming that is. The other thing I want to mention related to this sort of graph is I want you to look at the little black lines at the top or at the bottom of each column. And that represents our uncertainty. So for our greenhouse gases, you can see that we have about 2.5 watts per meter squared of extra warming. And then that little black line says, but it could be anything up to maybe 2.7, or it could be anything sort of down to 2.4. That's our uncertainty. That's what we that could be the range of our answer. So I'm going to ask you a question, which is that one of those forcings, those drivers, which of those columns has the greatest uncertainty associated with it? So I'm going to read it, and then we'll look back at the diagram. So first of all, carbon dioxide concentrations, solar irradiance, so output from the sun, albedo, which is our surface change, or aerosols. Okay, can you remember those four? So greenhouse gases, solar, land use, or aerosols. So if we go back now, and I'm going to ask the question, so which of those four has the biggest error bar associated with it? So solar, which is at this end, land use, which is at albedo. Oh, the letters, that's right, you need the letters, that's quite important, isn't it? Sorry, it's a Friday, I'm also somewhat asleep. That will help. Okay, a few more seconds. I think that's more or less everyone. Okay, let's take a look. Absolutely, aerosols. So if we go back for a second, you can see that for solar, we do have quite a bit of uncertainty associated with that, but it's not huge. The same for land use. But look, all of these things are aerosol related, and especially our indirect effect is huge. We basically don't know in a lot of those cases whether it's actually adding energy or cooling us down. And so aerosols are something that's still a bit of a mystery. But in reality, we can see what's happening, and that is our big greenhouse gases. So let's have a look at how those have changed. So here's a lovely ice core record, and this is taken from Antarctica. And it shows sort of 1, 2, 3, 4, 5, 6, the 800,000 years or so of our record. So 800,000 years starts over there, and then here is today. And you'll see that we've had to add a little bit to our scales, because at the top there, you can see what these values were in 2007. So it's not just CO2 that's a greenhouse gas. Remember, we also have methane, we also have nitrous oxide, and all of those have increased. The reason we talk so much about CO2 is because there's much more of that in the atmosphere than there is of these other two gases, even though methane is really very powerful as a greenhouse gas. So you can see, compared to what we used to have maybe sort of 700 parts per billion of methane. Today we're at 1,750 parts per billion. Had a huge impact on methane. For CO2, we used to have maybe 300 or so parts per million. So 300 molecules of CO2 for every million molecules of sort of gases in the atmosphere. And today, well, this is way out of date now, because that says 370, and last year we were at more like 400. And then you can also see that nitrous oxide has increased. So we've had a big impact, and we've got higher values today than we can see for 800,000 years at least. So how has that happened? Where has that come from? And we're going to focus just on CO2 for now. So first of all, and most obviously, we have fossil fuel burning. We've added maybe 280 gigatons, okay, it's a lot of tons, to our atmosphere since 1900, and we're adding maybe 6 to 7 gigatons per year. And the amount that we've been adding through fossil fuel burning has been accelerating. It's not a nice straight line, it's a curve. Okay, we're adding more and more and more each year. The other thing that we've done to add carbon dioxide to the atmosphere is we deforested very, very large areas. So you can see the map here shows the US in 1620, and those green areas represent forests. And as people arrive from Europe, you can see that a large amounts of those forests were cut down until we got to maybe 1920, and you can see that the whole East Coast has effectively lost its forest. Okay. Today that's less of a contributing factor. We're maybe getting 0.5 to 2 gigatons of carbon per year, and it's not the US anymore. It's other developing countries around the world, often rainforest countries that are generating that now. So the question is, where did all of that carbon go? And in reality, if we look at how much is in the atmosphere and we add up how much we've sort of added, then it seems like only about half of what we have burnt is still in the atmosphere. Half of it has actually gone somewhere else. So where else can it go? Where else has it gone? Well, first of all, a good chunk of that has gone into the oceans. And this is not necessarily a good thing, because it's acidifying our oceans. We're sort of dropping our pH of our oceans. But a good chunk of that carbon that went into the atmosphere has dissolved in the surface ocean. And especially in the North Atlantic, those colors there represent the fact that we've got a lot going in and it's actually sinking further down. So we're storing a lot of that carbon. Okay? Where has the rest of it gone? Into the biosphere. We've already talked about this process of CO2 fertilization, that plants it's more easy for them to take CO2 out of the atmosphere when there's more up there. And also, although we cut down a lot of forests in the US, more recently, in a lot of places, those have been regrowing. So for example, this shows Massachusetts in 1985 and in 1998. Oh no, sorry, I thought that was quick. In 1830 rather, and 1985. So you can see that actually a lot of forest has been added back to that state. And also in California, we're seeing this as actually a problem with our forest fires. We've been preventing forest fires for sort of a few decades now, and that's thickened our forests. And of course, that means that when we do have fires, they get much more intense, and so it's not necessarily a great thing. It's not how the ecosystem would usually work, but that has at least stored some extra carbon in these regions. So the question is, can we count on our oceans and our biosphere to continue doing this? And I put it emphatically, no, we can't. Especially if we're adding more and more and more CO2 each year, then there's a limit to how much of that CO2 we can put into the oceans and we can put into the biosphere. And why is that? First of all, the oceans can just become saturated, and also the warmer they get, the less CO2 we can get dissolved in them. And the second reason is that we can't grow forests everywhere. We can't grow forests out in the Mojave, in the desert, because we don't get enough rain. There are other things controlling how much of the biosphere can grow in certain locations. So we just can't keep growing huge areas of forest. That doesn't happen. So we really need to think about this. So now we're going to move into thinking about what might happen in the future, because it's really a very important question. So I've mentioned models a couple of times, but I wanted to show you a nice sort of image of what these actually sort of physically represent. So these models include an enormous amount of complicated interrelationships. We have things like the land, we have the atmosphere, not just as one solid block, but you can see that we have lots of different blocks representing different heights in the atmosphere. We have the ocean, and not just the surface of the ocean, but we have lots of blocks representing the full depths of the ocean as well. And then we have things like the ice that's around. We have biosphere, and that biosphere will change within the model depending on how much rainfall and what temperatures there are. We have things like the cycling of water and energy and carbon through our model as well. And so those little boxes represent little discrete sort of boxes, and we have to add energy or add carbon and take it away. And so these things are very complicated, really complicated. But they are an amazing representation, actually, of our climate system. I'm always amazed at how well they do work. They're not perfect at all, but they do work well. And this shows how far they've come. And for those of you that ever play really old computer games, like with the really blocky, like Donkey Kong things, that's really what our models used to look like. So FAR up there stands for the first annual report. That was the first big of those IPCC reports that came out. SAR was our second one, and you can see that already we've got better resolution, we've got smaller blocks, we can more accurately represent the system. Our third is the TAR, and this is the fourth one that came out. And of course, in this year, we're getting the fifth report coming out, and again, they're a little bit better. So we've got better at representing the system in our models, and we've also just got better and better sort of computing power to be able to do this. Because there is no point running a computer model of climate that takes longer to compute than the climate actually takes to change. Okay? There's no point running a model that takes 120 years to tell you what climate will be like in 100 years. Okay? So we do have some way to go still. It's not perfect. But the key thing is with these models is that we have to put in certain information for them to tell us anything helpful. And really what they need to know is how much of those greenhouse gases are we realistically going to add to the climate or to the atmosphere in the next century. And that's not something that we as Earth system scientists necessarily can answer for you. This is something where the politics, the economics, the social factors come in. And so all we can do is say, this is the range of possibilities. So we'll take a look at these. So this is what these different lines represent, and they're called RCPs, which stands for Representative Concentration Pathways, which is a real mouthful, so I'll just call them RCPs. And really they're just plausible, sort of possible futures of sort of how much greenhouse gases we're going to emit based on things like how our population might change, how we generate our energy, whether we stick with fossil fuels or whether we switch to more renewable. Whether we continue with our economic growth or not. So all of these factors play into this. And do you remember we said that the amount of extra warming that was happening about now is maybe about 2.5 watts per meter squared? Yeah. So what these do, what these different numbers are, and what these different colors represents, is different amounts, that 2.5 watts per meter squared. What will that be like actually by 2100? And our best case scenario, our nice sort of green line there, says it's going to be more or less the same as what it is today. It's going to be about 2.6 watts per meter squared by 2100. If we carry on as normal, if we burn everything we can find, then obviously that's not going to be the case. We're going to have much higher greenhouse gas concentrations. And so our worst case scenario is something more like that blue line, that RCP 8.5. And what that says is, okay, we have 2.5 watts per meter squared today. By 2100, we're going to have 8.5. Okay? So obviously, our green line is our best case scenario. Our blue line is our worst case scenario. And what we want to do is see what climate will be like if we follow both of those trajectories. And then we want to try and persuade people to follow the one that we'd like. Okay? So let's look a little bit in more detail about what those actually represent. So on the left here, we have population. And it's in millions, so 600 million, or 6,000 million is 6 billion, okay? And so according to our sort of best case scenario, our green line, then population would peak in maybe about 2050 and then stabilize and perhaps taper off a little bit. So we hit maybe 9 billion, which is pretty reasonable, okay? With our worst case scenario, we don't really ever hit a maximum and taper off. We just keep increasing, and so we've hit 12 billion easily by that 2100. We can also look at these different scenarios based on how we get our energy. So in the year 2000, those different colors represent how we generated energy on Earth. So that black is coal, the orange is oil, that sort of greeny, bluey color is natural gas. And then all of those other ones, so nuclear, bioenergy, hydro, solar, those are somewhat more renewable. They're certainly not fossil fuels, at least. And then we can see that in our best case scenario, our RCP 2.6, we still have to generate a lot more electricity, a lot more energy to satisfy the world population. And much, much more of that is coming from those renewable sources. And look at that change. So in 2000, maybe 80, 90% of our energy comes from fossil fuels. If we want to follow that best case scenario, by 2100, maybe 30, 40% needs to come from those more sort of renewable or less fossil fuel sources. If we go for our worst case, in our worst case, we're just burning everything. We're just carrying on as if we don't care. And so we burn enormous amounts of coal, oil, natural gas. We have to massively expand nuclear as well in order to meet that energy demand. Okay? So it's not just how we generate that electricity or that energy, but also how efficiently we use it. And this is what happens to our CO2 as a result of those patterns. So on the graph on the right shows that if we follow our best case scenario, we stick about 400 ppm, which is about what we are today. We increase a little bit in the next sort of decades and then decrease again. Our worst case, you can see what happens. We just massively increase up to maybe 900, 1,000 parts per million. And really the last time that CO2 was that high was maybe 40, 50 million years ago. We're talking enormous changes. But let's think about this realistically. This is the amount of emissions per year that we can produce if we're going to follow those different tracks. So our best case scenario here in green, what that means, if we're going to follow that trajectory, we need to peak in terms of our emissions by 2020, 6 years from now. We then need to start reducing our emissions and get to basically zero by 2080. No comment. But you can see that with our blue, we just keep increasing each year. And right now, from when they did this in 2000, we've been following the blue line. They're more or less very close together right now, but that's the one we're following. So my question for you is, let's see how optimistic you're feeling. Which of those do you think is more likely? Best case, worst case, somewhere in the middle. What do you think? There's no right answer for this one. Just curious. So a few more seconds. Okay, let's take a look and see. So you're not feeling terribly optimistic. We're leaning as a class towards the higher end. So hopefully a lot of us think that we're not going to hit that really worst case scenario, but we're still going to be emitting quite a lot of CO2 and building up a lot in our atmosphere. So that's nice, and it's all pretty academic right now, but let's have a look at what those changes would actually mean. So keep track of your particular RCP. I think a lot of the images I show only has sort of the best case, that green line, versus the 8.5, the blue line, but you can see the difference that it makes. So first of all, let's look at temperature. So we've already seen a change of maybe 0.86 degrees Celsius above where we used to be. But if this is what will happen by 2100, if we follow the best case in blue, we get an additional change of about maybe 1.5 degrees Celsius. If we follow the worst case scenario in pink, then we get something more like 4 degrees Celsius. And the range associated with them, that sort of colored band either side, is if we run lots of models, they give us slightly different answers each time, and that sort of shows the uncertainty with that. But most of them sort of center out about 4 degrees Celsius. And that doesn't sound like a lot to us, because we're used to seeing that like between, say, 8 o'clock in the morning and midday, perhaps. But this is the whole planet warming up by 4 degrees Celsius, or 6 degrees Fahrenheit. I did put it up there. And that is a really astounding change. Because if we think we had the Little Ice Age, remember I mentioned that, and we walked on the Thames, we had sort of medieval warm period where we had sort of more vineyards further north. That noise of that Little Ice Age and everything else is all encompassed in that red line there. And that is what those predictions look like compared to the temperatures over the last 1,000 years. This is an amazing change, and it's happening ridiculously fast. And that's a problem for our life on Earth, because they can't necessarily move. Trees can't move distances like that. They can move over thousands of years, and just sort of successive generations will move a little bit north or south, but they can't change in the sort of timescales we're talking about. And so, suggested reading, there's a really good book, and this is written by Mark Linus, and he basically collected together a lot of the research that has been done, saying what the Earth would look like with a 1 degree Celsius rise in temperature, or a 2 degrees, and then he has a chapter for each of them up to, say, sort of 6 degrees Celsius, which is really catastrophic. But if you don't want to read the whole book, because it's not necessarily easy reading, there's a 5-minute YouTube version. So there's really no excuse not to at least have a look, because I think it's really actually astounding, and I think it really drives the point home about what that sort of 4 degrees change actually means. So I really would encourage you to watch that over your nice long weekend. Okay. And do you remember on Wednesday I said that that warming isn't spread evenly over the whole Earth? There's certain parts of the Earth that warm more, and we warm more over land and also at the high latitudes. And that's the same thing if we're going to look at future changes. So my figure on the left shows our best case scenario, and we're still seeing changes in the Arctic where that more extreme temperature rise happens of maybe 3-4 degrees Celsius, and that's really big. Around us, we may be getting another 1.5. This is what happens in our worst case scenario. In this scenario, we're seeing much more like 9 to 11 degrees Celsius. And in terms of, say, pick 2 cities in the US that have an annual average temperature that different, it's maybe somewhere down in Mississippi versus somewhere up in Minnesota. That's a very big change in our temperature in just 100 years. And you can see even around us in Southern California, we're seeing 4-5 degrees Celsius temperature increase, which is just huge. Precipitation is much, much, much more difficult to get at. Our models have a much harder time agreeing on that, and it's just a more difficult thing to model. But in general, the pattern seems to be that we will have much more of a contrast between wet and dry seasons, and we'll have much more of a contrast between wet and dry places. And so if you're dry, you're going to get drier. If you're wet, you're going to get wetter. And so this is why we say that there's more likely to be increased floods and droughts in the future. And obviously, the more extreme our scenario, the more extreme the changes that we see. Sea ice. So this is what happens to our sea ice with those different patterns. And to be honest, it's not good news for either of them. With our best case scenario, we maybe continue to lose sea ice, but it stabilizes at maybe about half what it was. And that's our best case scenario in blue. In our worst case, it's gone by maybe 2080 in the summer. It'll still be around in the winter, but it's gone by the end of by the summer, by 2080. And what we're seeing today is changes that are happening much faster than our models would predict. So that's really an upper limit, we think. And that's what our world will look like. I think it's worth showing this map. This is what the sea ice would look like today in the summer. Our planet could look really different within your lifetime, So, sea level rise. Anyone live on Newport Beach? A few people, or at least one. So this should be something that you pay very close attention to right now. So sea level will be rising, and that's, remember, because our seawater is expanding as it warms up, but also because of contributions of ice melt. And this is what our projections show. Our best case scenario, remember, this is the minimum. This is us peaking in 20 years and stopping all emissions by 2080. With that scenario, we still see an increase in sea level of maybe 45 centimeters. And for somewhere as low-lying as Newport Beach, that's a problem. Not necessarily every day, but the next time there's a big storm, then you're much more likely to get flooding. Our worst case scenario, and really I think this is still an underestimate, is something more like that. More like sort of 75, 80 centimeters. And that's pretty substantial. Okay. And there's a really cool little link there, which allows you to zoom in on parts of the US, and they've taken sort of a topographic map, and they can show you how much of your little area will be flooded by 1 foot, 2 foot, 3 foot rise in sea level. So that's a really interesting one if you want to go to have a look. So here's a geography question for you, and for the people from ESS 1, don't give the game away. Which is the US state that has the lowest average elevation above sea level? which is our lowest lying state. And if you're from overseas, feel free to consult the person next to you. Oh, and it has A and B. Oh, I forgot to fix this from last quarter. Sorry, it should be A, B, C, D. Don't get 2 votes for the same answer. Okay, a few more seconds. You either know it or you don't, I think. Okay, so let's see how good your geography is, all you American people. So we have a tie between Florida and Delaware. Florida just won, but they would be wrong. Delaware is our flattest or our lowest lying state on average. Okay? And why is that important? I went to a talk by someone who studies ice cores, and I think I really loved his little statement, which is, for all of you Americans, do you know which was the first state to ratify the Union or something like that? I don't know my history. Delaware, thank you, yes, it's pretty obvious. So Delaware, so he was saying that Delaware is going to be in real trouble, even by the end of the century with those small sea level rises. It's going to be in trouble. It's a coastal state. And so he said, first in, first out. Okay, and so it's a real problem. What are they going to do about this? And it's not just Delaware, but Florida is also really low lying. And so this, a little couple of maps. So this one, first of all, shows how much of the US, especially the East Coast, which is sort of shallower, how much would be flooded by a 1 meter sea level rise, which is in red, and how much would be flooded by a 6 meter sea level rise in orange, which remember is what happened at the last interglacial period when temperatures were pretty similar to today. So Florida is not in a good way, and in particular, Miami is in real trouble. So this is Miami. And you can see that the blue areas there are what would be flooded by a 1 meter rise in sea level, which is towards that top end by the end of the century. And you can see that basically it's just a whole chain of islands. And those chain of islands are also not going to be that much above sea level. What happens when the next big hurricane comes through with sort of storm surges of 3-4 meters or so? It's screwed, basically. And they got people from the Netherlands who have a very low-lying country and have been working for sort of centuries to protect their coastline. And they got them to come over and take a look and see what they could do to protect the city. Like, tell us what we need to build to protect our city. And they just said, you can't. It's on really porous rock. That water's just going to come in. And so Miami's in real trouble, and I don't think they necessarily realize it yet. So don't buy a house there. Okay, but I think we can sort of laugh about it to a certain extent here because people can go somewhere. But I think the really sobering thing thinking about sea level rise is that we have countries that look like this. If they see 1 meter of sea level rise, there's nowhere else they can go. So we are basically talking about wiping out entire countries, potentially by the end of the century, and denying them the right to live where their ancestors lived and continue with their way of life. And I think that's something that we really don't think about enough, that we do have this responsibility to some of the people for the way that we're living. And that's also true of places like Bangladesh. Bangladesh is an enormously populated country, and it's really low-lying, and they have big rivers that run through, and they can flood very easily. And a 1 meter sea level rise would do that to their country and displace a huge number of people. Maybe 200 million people worldwide would be displaced by a 1 meter rise in sea level. Where would they go? We have enough trouble with a few 100,000 sometimes. And I do think, and these sort of countries, so Bangladesh, those island countries like the Maldives, Tuvalu and the Pacific Islands, they're really leading the way in saying, no, let's not just sort of talk about what we can do to adapt to climate change. We need to try and stop it. We need to try and take action now. So they're often leading the way. So the other thing to do with the oceans that doesn't ever get talked about, and it's really nothing to do with climate change as such, it's to do with still that elevation in CO2 in the atmosphere. And that is our pH of our oceans is changing. It's already changed by 0.1 pH unit. It's become slightly more acidic. And that may not sound like a lot, but remember it's a log scale. So that's actually something more like a 20-30% increase in the acidity. And if we sort of stabilize our CO2 emissions, then the nice thing is that our pH doesn't change anymore. But if we follow that worst case scenario and keep pumping CO2 into the atmosphere, as that level of CO2 rises in the atmosphere, our pH drops. And you can see that the level of uncertainty we have about this is really nothing. If you can tell us the CO2 increase in the atmosphere, we can really tell you very precisely how much the pH of the ocean will change. So instead of talking about how much temperature rise we are willing to deal with, perhaps we should be instead talking about how much of a pH shift should we see in the oceans, because that has a very strong effect on corals. Corals are basically gone if we see 0.4 pH unit change. They're not going to be able to deal with that. And so obviously we see our ocean temperatures increase as well. So here's a little cheerful summary of all of those things. I told you it was depressing today. By 2100, this is what we can see. This is a best case and worst case. 400 to 950 parts per million of CO2 in our atmosphere. Our temperature will be anywhere between 1.5 to 4 degrees warmer. The poles will be much warmer than elsewhere, or will warm more than elsewhere, rather. Dry areas drier, wet areas wetter. Cryosphere will continue to melt. Sea level will rise because of that warming, but also because of that additional melt. The decrease in the ocean pH, and things like changes in the timing of our seasons, increases of floods events, increased in intensity of certain storms, things like that. So it's not looking good. And in terms of things that might sort of interest you more directly, things like our water supply, our ecosystems, you can see that even if we increase our temperature by 2 degrees Celsius, which sounds like nothing, we could potentially be losing nearly a third of our species on Earth, a third of our biodiversity with 2 degrees. And as we increase, it just gets worse and worse. So that's there. Also, there's things like health. The fact that we're going to be exposed to sort of malaria in areas where it hasn't been able to exist before, because now those mosquitoes can get there. Increased sort of illnesses and deaths from heat waves, from air quality issues, things like that. So it's a real change. So I don't want to pretend that we know everything for certain. You can see that there's ranges of uncertainty. But I think it's interesting to look at where those uncertainties are. So first off, in the response of clouds and precipitation, I said that's really difficult to model, and we're trying to get better at that. Potential for sudden shifts in our climate. So for example, you saw that our sea ice doesn't sort of nicely decline gradually. It sort of declines a little bit, there's a rapid drop, and then it sort of levels out again. So where are those going to occur, and how will they affect us? And that's really to do with a lot of the cryosphere. Ice sheet volume loss, and this is a big one for sea level rise. If you speak to a lot of the experts on sea level, they don't think that that upper limit of 0.75 meters is actually what we're going to see. They think we're going to see much more than that. And the question is how quickly will that happen? That's our real question, and that's what we'd love to know if we could. So what can be done? What can be done? The main thing we have to do is reduce our CO2 emissions. There's no way of getting around that. And so this map shows the countries that have committed to the Kyoto Protocol, which is the countries that have committed to lowering their CO2 to 1990 levels. And you may see that there's a bit of a change of color near where we are. And that's because Canada signed it, but actually they've withdrawn now from it a couple of years ago, because they found their tar sands, which produce an awful amount of fossil fuels and carbon. And the US is really the one country around the world that signed it but never ratified it. They never signed up to having to actually sort of obey those standards. So I don't think that's terribly good. Individual cities around the US have done a lot, and they've individually signed up to committing to reducing their CO2, but as a country, the US hasn't yet. And this is I put in because a lot of people say to me, well, it's okay because we're going to run out soon, aren't we? So then we'll have to find a way of switching. And this is one of the graphs that you're going to look at for your quiz this week. In purple, you can see what we've used of our oil, gas, and coal. And in blue is what we have left. So yes, we're working our way pretty well through our oil, and obviously we've been accelerating how much we're using. But look at how much coal we have left. We have plenty of fossil fuels left. We're not going to reach a point where we have to switch. It's going to have to be a conscious decision to move to different methods of generating electricity and energy. So things that can be done, things like reforestation, or at least stopping the deforestation of certain areas. Switching to alternative energy sources. Much more efficiency. We are not necessarily so efficient. So start turning out your lights and not idling your engines for quite so long. Changes to farming methods would be a good one. Carbon sequestration is where we actually take CO2 out of the atmosphere and find a way of storing it somewhere. People have suggested the deep ocean, or people have tried pumping it back into oil wells that we have emptied out. And then geoengineering, crazy things like giant space mirrors, which we're centuries away from being able to build, and also wouldn't prevent things like the pH of the ocean changing or anything else like that. Okay? And these are all things that could be found in those other 2 chapters. So if you're interested, go find those. So don't read those now. I put them there for your notes. And I just want to talk about the top one. The world is not going to end. We are not going to cause the extinction of the human race by melting all of our ice. We can definitely support less people if we do that. It won't be as pleasant a world to live in. And so really our choice is sort of a moral one, is whether we're willing to deal with that. Okay? And it's also worth making the point that the world doesn't end in 2100. And that's all we ever talk about with climate change. Because we're still going to have a human civilization, hopefully, after 2100. We're still going to need energy. Where are we going to do that? How are we going to do that? How much more climate change are we going to commit to if we don't actually change our plans? Okay, so on that cheerful note, we'll talk about snow on Wednesday. Yeah.